So the fundamental theorem of calculus is basically the topic that brings the first topic of study, which is derivatives, together with the second topic of study, which is integrals. So we're moving into the second topic of integrals. So there's two different parts to this fundamental theorem of calculus. There's part 1 and part 2. Part 1 says that if f is continuous on the interval from a to b, then the function big f of x, that's how we denote an integral, is equal to the integral of little f of x dx. Okay? So basically, big f of x is your function that you would get if you integrate little f of x. Now, this is the part 1 part, so that's not that surprising other than the notation. But we also can find that the derivative of f with respect to x is equal to the derivative of the integral from a to b of f of t dt. And basically, for this, you would get that the derivative of that integral there will be f of x. Okay, so what I like to think about with part 1 is that you have a derivative and you have an antiderivative, and they're almost like inverse functions where they will cancel each other out, and then you just get that integrand that's in there. Now, this is only the case, and this is really important to note, this only works when your a, or your lower bound, is a constant, and your b, which is your upper bound, is equal to a single variable. If there's anything else there, or if that order is switched, then different things happen. Okay, so let's give a couple examples. The first example, the derivative of this antiderivative from negative pi to x of cosine t dt. Okay, so it met the criteria that I said on the previous page. So the constant's on the bottom, the constant's the lower bound, the variable's the upper bound. So when you take the derivative of this, you are going to get that this is equal to cosine of x. And that's it. Okay, derivative, antiderivative, and they will cancel each other out. They're kind of like inverses, and you get just the function. Same thing here. So we've got our constant on the bottom. We have the variable on the top. Plugging that in, I will get 1 over 1 plus x squared. So derivative of an antiderivative, as long as the constant's on the bottom and the variable's on the top, you are good to go. Now, if you've learned anything in the past couple months, you know that it is not this easy. So how about something like this, where we still have the constant on the bottom, which is really good, but now we have an x squared. Well, I can't deal with that x squared up there. That we can't take the derivative of that antiderivative when you have the x squared up there. So what we're going to do is we're going to use a little chain rule, or a little u substitution with chain rule. So I'm going to say my u is x squared, which leaves my y the integral from 1 to u of cosine t dt. Okay, now with chain rule, we know we have to find the derivative of both of those. So u prime will be equal to 2x, and y prime, so the derivative of this integral right here is going to be cosine of u. Now with chain rule, we're going to multiply both of those things together. So we would get 2x cosine of u, which will be 2x cosine of x squared. Okay, so derivative of an antiderivative, if it's from 1 to a variable, then you just go ahead and plug that variable in, and you're into the integrand, and you're done. If there's anything else, then you have to do a u substitution. Now, you may be able to just notice that the x squared just goes, or the x, whatever that is, just goes in for that t right there, and you multiply by the derivative of that. Now, part D is one I don't think you would ever see on an assessment, because you're like, wait, there's whoa, there's variables in both sections. We can't have that. But I thought it might be a good one to just go through really quick. So in the last video, we talked about the additivity rule. So I'm actually going to rewrite this integral. The integral, I'm going to leave the 2x there, but I'm going to pick any number you want. I'm just going to have it go till 0. It does not matter. You could pick any number, pi, 100, 5. It doesn't matter. Just leave You'll see why. So plus e to the t dt plus the integral from 0 to x squared of 1 over 2 plus e to the t dt. Okay, so additivity says as long as the number up here and the number down here are the same, then you can add those two integrals together. You can combine them together to get one big interval, but we're just going to work with the two separate ones, okay? Because now I have variables and constants, which I did not have over here. Now this one has a slight issue because the constant needs to be on the bottom and the variable needs to be on the top. So I need to switch those. So we also saw this in the last video, that you can switch your bounds by negating your integral. So 0 to 2x of 1 over 2 plus e to the t dt plus the integral from 0 to x squared of 1 over 2 plus e to the t dt. Okay, now we would go through this using a chain rule, but basically said and done. You can go through this the long way if you want to. What we do is we bring down that negative right there, put the 2x in for that t, so 1 over 2 plus e to the 2x, but because it's not a single variable right there, it's a 2x, we need to multiply by the derivative of that 2x, which is 2, and that comes from chain rule. And then plus, same thing over here, 1 over 2 plus e to the x squared, so I just replace that t with an x squared, and then that's going to be times 2x because that's the derivative of that upper function there. Okay, so these are derivatives. So I'm finding the derivative of each one of these. And remember, derivatives and antiderivatives are inverses. This one right here is my least favorite type of question. You'll see why in a moment. Because there's no real answer to it. In the end, you're going to end up with an integral, and most of us want an actual function. So here's the deal. The derivative has to be tangent of x. So I'm going to put a 3 right here, and then an x up there. So right now, if you think about what we've been doing so far, the derivative of this integral, so let's check it over here. If we did the derivative of the integral from 3 to x of tangent of t dt, that would be equal to tangent of x, okay? Because they would cancel out, the x would go in for the t, done. So it satisfies that condition. Now it also has to satisfy the condition that f of 3 equals 5, and that's why I put the 3 there, because then if you put a 3 at the top, you get 0, but I don't want it to evaluate to 0. I want it to evaluate to 5. So what I'm going to do is put a plus 5 here on the end. Now that actually won't change anything because the derivative of 5 is 0, so I still get my derivative. If you plug in a 3 up here, the integral from 3 to 3 of tangent of t dt, that's 0. So remember, that was our 0 rule. So it meets the conditions. So here's my final answer. Again, you're not going to like it because it has a tangent left in it and an integral. Not the tangent part, the integral part, but that's just how it is. Okay, so part 1 was all about derivatives of antiderivatives. So now we're going to go into part 2, and part 2 is a little bit more fun with our integral evaluation theorem. So basically what this says is you've got your bounds, and when you're done, you're going to get a big f of x. That's my integral, and then I'm going to take and evaluate the integral, the antiderivative, f of b minus f of a. Now, we've actually seen this before. We saw this. Let's go back one more time to that lovely train question from 7 to 9, right? So I have the integral of 75 dx from 7 to 9. Right? And we said that the integral of that would be equal to 75 times 9 minus 7, which is equal to 75 times 9 minus 75 times 7. So that goes back to that. We've seen this. We're just now formalizing it. So we need to find our big f of x, and then we need to evaluate it at 9, and then at 7, or the upper bound, the lower bound, and then we subtract them. So now I'm sure you're all excited to know what the power rule of antiderivatives is. If you did the activity in class, then you probably are aware of what it is, but we're working backwards here. So instead of subtracting 1 from my exponent, I'm going to add 1 to my exponent. So with derivatives, remember, if we had the derivative of x to the n, we said that that was n x to the n minus 1 power. Now we're just going to work opposite, right? We're going to add 1. Instead of multiplying that, we're going to divide by that new exponent. Okay, so you add 1 to the exponent and you divide by the new exponent. Let's give an example. And this one right here, let's just use that additivity rule really quick. Not additivity, the sum rule. So we have negative 1 to 3 of x cubed dx plus the integral from negative 1 to 3 of 1 dx. If you don't mind, I'm going to say 1x to the 0. You'll see why in a second. Okay, so now our new power rule says you add 1, so it becomes x to the 4th, and then you divide by 4, which, by the way, if I came over to here, x to the 4th over 4. Now, if I differentiate that, right, the 4 would come down in front, 4x to the 3rd, and then divide by 4, which is equal to x to the 3rd, which is where I started. Okay? Plus, now this one up here is x to the 0, so we add 1, and then we divide by that new exponent. That right there is what my big f of x is, and now I'm going to evaluate that from negative 1 to 3. Okay, so I need to find f of 3 minus f of negative 1. So I'm going to have 3 to the 4th over 4 minus, plus 3 minus negative 1 to the 4th over 4 plus a negative 1. And then you just type that in the calculator and you get your answer. Same thing for this one. This one's a little trickier because I believe we've got this one says specifically find the area. It's not just the integral. So what we want to do for this is we want to, areas always have to be positive. So we're going to find out where it crosses, which is at 2. I'm going to do 2 separate integrals here. I'm going to do the integral from 0 to 2 of 4 minus x squared dx. And then I'm going to add to that the integral from 2 to 3 of 4 minus x squared dx. But that answer is going to be negative, so I'm going to absolute value that. And that's only because of that word area, and the area always has to be positive. Okay, so let's just work on this first one. So for the antiderivative of a constant is going to become 4x minus, and then we've got x to the 3rd, x squared, so we're going to add 1 to our exponent, so that becomes x to the 3rd over 3. That's my antiderivative. That'll be the antiderivative for both of them. So now we're going to evaluate. So I need to find f of 2 minus f of 0 plus, and then it's going to be the absolute value of f of 3 minus f of 2. And again, the reason for that is because it specifically says area. So what does this look like when it's all plugged in? We're going to have 4 times 2 minus 2 cubed over 3 minus 4 times 0 minus 0 cubed over 3. And then plus, and I'm running out of room, so whatever you get over here, just absolute value your answer. There's Mr. Shore. Okay, now, really important, this last question. So this last question comes up so often on AP exams. So I just wanted to bring you through it really quick. So my piece of advice is whenever you see something like, well, make sure you read very carefully. So it says the graph of a continuous function f is shown below. So this right here is the graph of f. Now, we are going to be talking about h, and h of x is the integral from 1 to x of f of t dt. So first off, it's going to say find h of 1. So plug 1 in for x. So therefore, we'd have the integral from 1 to 1 of f of t dt, which I actually don't need to go any further with that question because we know when we have the same upper and lower bound, we have no area under the curve, so it'll be 1. Okay, is h of 0 positive or negative? Okay, so we're going to plug that in. So we have the integral from 1 to 0. So all I did was look at this h of x, and it says plug x in for 0 of f of t dt. Okay, so from 1 to 0, so that's my first issue. It should be lower bound to upper bound. So I'm going to negate my integral and make that from 0 to 1 of f of t dt. Now, if you look over here, from 0 to 1, there's positive area there. So I would have a negative times a positive. And that's also because I'm starting at 0. So 0 is 0. And then I have positive area that I'm accumulating here. So therefore, my answer will actually be negative. H of 0 is negative. Okay. Find the value for x, which h of x has a maximum. Okay, so when do maximums and minimums happen? Maximums and minimums happen at critical points, which is when the derivative equals 0. And then we're going to sign pattern picture and figure out where we have critical values to become maximums. Okay, so we need to find the derivative. I'm going to move down here for a second. So I need to find the derivative of h of x, which will be the derivative of the antiderivative from 1 to x of f of t dt, which will be f of x. So the derivative of h of x is f of x. The derivative of h of x is f of x, which is my graph over there. Now, I need to do a sign pattern picture with my critical points. Critical points is when your derivative equals 0. Again, the derivative of h of x is f of x. So you're looking at a derivative graph right now. So it equals 0. My critical points are 1, 4, and 8. You're looking at the derivative. Okay, so now before 1, my derivative graph is positive. It's above the x-axis. Between 1 and 4, it is also positive. It's above the x-axis. Between 4 and 8, my derivative graph is negative because it's below the x-axis. So find the value of x for which h of x has a maximum. So a relative maximum could be occurring right there. We should probably actually consider endpoints as well. We know this is 0. So this would be a little bit below 0, but I increase, and then I do a lot of decreasing. So at 4, I would say you have a maximum. And the reason why you have a maximum is because h prime of x equals 0, and h prime of x goes from positive to negative, which means my h of x will go from increasing to decreasing. Find the value of x for which h of x has a minimum. So it's the lowest value that I obtain. And look at all of this that we don't have a relative minimum, but we will have a minimum at x equals 8. And that's because if you look here, you start at 0 here. So this is slightly negative. Then we increase until we get to here. Then we start to decrease, and we decrease a whole lot more than we increased here. So we're going to go past the point where we started at 0. We're going to keep decreasing because this area is a whole lot more than that area right there. So we'll decrease down to that point at x equals 8. Okay, and then last but not least, it says find the coordinates of all the points of inflection. Okay, so I'm going to erase some of this. Where can I erase? Okay, so points of inflection happen when the second derivative equals 0. So when h double prime of x equals 0. Okay, well, if h prime of x, so we saw that here, is f of x, then h double prime of x is f prime of x. So now we're going to be talking about the slope here. Okay, so your possible inflection points would happen when your slope equals 0. Okay, so my slope equals 0 at x equals 1, 3, and 6. Now, they do have to change direction, change concavity, and they do, because if you notice here, it goes from concave down to concave up, because my second derivative would go from negative to positive, and then positive to negative, and then negative to positive. So all three of those would be points of inflection. So, fundamental theorem of calculus, part 1 and part 2. So part 1, if I can scroll back up here to the top, basically just says you can do a derivative of an antiderivative and you get the function back. Now that's only true if there's a constant as your lower bound and a variable as your upper bound. If those are switched, then you need to switch your bounds using a negative, and you may also need to use a chain rule substitution technique. And then last but not least, you have fundamental theorem of calculus part 2, and this is called an evaluation theorem, and that's basically where you find your antiderivative. As of right now, you're only using the power rule for antiderivatives, which is add 1 to the exponent and divide by the new exponent, and then you need to evaluate that at the upper bound and the lower bound. Please pay close attention to that last question. We will do tons of these in class because it is definitely a possible free response question.